take a look at the next family, the family of exponential functions. So we've looked at functions with exponents before, like functions like x squared, like 2x to the fifth plus 4x to the third, etc., right? But these are actually not exponential functions. So what is it about a function that makes it an exponential function? Actually, you notice that these guys, they all have the variable in the exponent. So that's what makes an exponential function. Okay, so those, the exponential functions are of the form y equals some base to the power x. And we only look at these where the base is positive, okay? Because if we look at something like -1 to the x, well, funny things would happen depending on if the exponent were even or odd. That would jump between positive and negative, and it would be discontinuous. So we only consider exponentials to be those with a positive base. So the goal is, can I come up with what the graphs look like for this family of functions? So I set up a little table here. Let's see if we can fill in the graph for 2 to the x. So we have to remember some exponent rules. Remember, the negative exponent flips the fraction. So 2 to the -1 would be 1 over 2. Remember, 2 to the 0 is defined to be 1. 2 to the 1 is just 2. 2 squared is 4. So let me plot at least some of these points. Let's see, here's -1/2. 0, 1, and 1, 2. Let's put 2, 4 on here also, might as well. And then I don't know, this one's close to the axis, right? -2 1/4. And then let me fill in this shape. Okay, so the more negative that x becomes going in this direction, well, I mean, I'd have like 2 to the -3, 2 to the -4, 2 to the -5. So these fractions are going to get really, really close to 0, but they're never actually going to become negative numbers. So actually, exponential functions have a horizontal asymptote, but they actually only approach that horizontal asymptote on one end, unlike how rational functions approach the horizontal asymptote on both ends. Okay, let me fill in 4 to the x. Let's see, 4 to the -2 would be 1 over 16. 4 to the 0s, 1. 4 squared is 16. Okay, let's see. 4 to the -1 is 1/4, so it's a little hard to fit these in. Let's label 0, 1, and then 1, 4. Okay, so something like that. So this is 4 to the x. This was 2 to the x. Okay, what about 10 to the x? I bet you can guess what that one's going to look like. Get a color for that one. It'll stand out. Let's do a green. Okay, 10 to the -2 is 1 over 100. Okay, let me see if I can at least plot a few of those. I'll have 0, 1 again. I'll have 1, 10. It's going to be way up here. And then -1, 1/10. So try to do a decent job drawing this. It's going to be even more steep. Okay, so my exponential functions there have the same shape, but the graph gets steeper closer to the y-axis there as the base increases. So what else can I say? Let's see, I guess I have one of these left to still do. What about e to the x? So e is a special constant, kind of like pi. So that's an irrational number, so it's called Euler's number. Euler's number. So it's a number that comes up often enough in applications that they've given it a special designation. So it's about 2.7. Okay, the digits go on, but for as far as graphing goes, that's about as precise as we're going to get anyway. So let's see if I fill these in. E to the -2 would be 1 over e squared. Let me see, what's 2.7 squared? So this is like 1 over 7-ish, 1/7-ish. Okay, e to the -1 is 1 over e. That's like 1 over 2.7. Pretty close to a third. 0 is 1. E to the 1 is about 2.7. And then e squared, I just calculated, 7.3-ish. Okay, let me plot these points. Okay, so e to the 0 is 1. E to the 1 is 2.7. And then e squared, 7.3. Okay, so try to draw this. I mean, same basic shape. Look very similar to 2 to the x, right? 2.7 to the x. Okay, so then what else can I say? Notice for all of these, exponential functions are friendly. The domain is all real numbers. Assuming the graph hasn't been shifted, we're going to look at shifts here in a minute. The range would be everything above that horizontal asymptote. And then these guys, you notice as you move from left to right, this function is increasing all the way across the domain. These functions are all increasing. Okay. So then, let's see. Well, we said that we only look at bases that are positive, but what about fractional bases between 0 and 1? So you see these ones up here? In this table here, all of the bases here were bigger than 1. 2, 4, 10, 2.7. So you see how these bases are bases in between 0 and 1? They're fractional bases. Let's fill out the table for those. So we flip the fraction. Okay. Let's see, so my points for that guy have -2, 4. This one I scaled 1, 2, 3, 4. I have -1, 2, 0, 1, 1/2, 2 1/4. Okay, so you can see I have the same kind of shape but this time the graph's decreasing. Okay, and this time I'm actually going to approach that horizontal asymptote on the right side, but it's still the same, y equals 0. Let's do a fifth to the x. Oops. Forgot to flip that, didn't I? Fifth to the negative 2 is 5 to the 2, it's 25. A fifth to the negative 1 is 5 to the 1. Fifth squared is 125. Okay, so I don't know that I'll be able to fit all of those. Let me plot at least these three. So negative 1, 5. Zero, 1. And then 1, a fifth. And so again, you can see I get the same shape, but decreasing more rapidly. So for the functions where the base is in between 0 and 1, I have the same kind of shape as for the bases bigger than 1. The domain is still negative infinity to infinity. The range is 0 to infinity, but these guys are decreasing across the whole domain. Let's look at some transformations problems. So now we know what this family of functions looks like. So when I see something like number 1, I go, well, I could really do this by transformations. I could say, I know the base graph, 2 to the x. We did that graph. Looks like that, right? Okay, then if I make the x negative, I'd have that graph. Okay, and then shift up 3. So I could tell you, I mean, pretty much immediately what that basic shape is going to look like. So I could go about the problem that way, doing transformations, or I could set up a table. So let me look at this table. So if you look at the exponent here, that's what's going to tell me if the graph has been shifted left or right. So since there's no addition or subtraction affecting the x there, this function actually hasn't been shifted left or right, okay? So that means I can use the center value in my table as just 0. Oops. So I could actually just plug in negative 1, 0, and 1. Let's see what I get if I do that. So 2 to the negative 1 is 2 to the 1. Oh, forgot the plus 3. 2 to the 0 plus 3 is 1 plus 3. 2 to the negative 1 plus 3 is a half. Plus 3 is 7 halves. And then let me just plot these points. So let's see, I've got negative 1, 5. Got 0, 4. Got 1, 7 halves. Okay, and then you can see the horizontal asymptote has been shifted up by 3. So let me make sure I include the horizontal asymptote, and then I can just fill in the graph. So these are pretty easy to graph. Okay, so there's the shape, and you can see that matches up with the shape we came up with thinking quickly about transformations. Let's see, so the domain of this guy is going to still be all real numbers. The range, however, is now 3 to infinity. Let's try another one. Let's do the same thing. Okay, so I'd start out, let's see, my base graph would be e to the x. I'd shift left 2. Oh, actually, I want to do the multiplication first. Didn't see that. That makes the y's negative. Then I'd shift left 2. Something like that, and then down 1. So, I mean, really roughly, the graph's going to look something like that. Okay, let me plug some values in. So how do I know where the graph is centered? Again, I'm looking at the exponent. I'm going to say what number would make the exponent 0? That's going to be my center value for my table. So in this case, the number that would make the exponent 0 would be -2. That's going to go in the center here then. So then I'll do -3 and -1. So let's see, I'll have negative e to the -3 plus 2 minus 1. So that's, I need to make some more room, 1 over e minus 1. So that's like around 1/3 minus 1. So like -2/3-ish. Let's do -2. -3.7-ish. Okay. Actually, probably need to move this down. Okay. All right, let's plot the points. Got -3, -2/3-ish. So I can even label that nicely. -3, 1 over e minus 1. -2, -2. -1, -3.7-ish. It's -1, -e minus 1. And then I need to put the horizontal asymptote, and I lost a negative. So here's how I know there's a mistake. So look at this. So my next step, I'm putting the horizontal asymptote on the graph. You see how the horizontal asymptote is y equals -1? So the point that I see that's off is this one. So let me look back at the table here and see if I can figure out what did I do funny in this calculation. I see what it is. I lost this negative. That's an easy fix. This should be negative, negative, negative. Okay, so I have -1/3 minus 1. It's actually -4/3. -1 1/3. All right, that looks better. Looks something like that. Okay, domain for all my exponentials, all real numbers. The range would be negative infinity up to that horizontal asymptote, -1. Let's see. I didn't label the y-intercept. I mean, I could. So I need to move this down a little bit. I'll put the y-intercept here. So if I wanted the y-intercept, I'd have to plug in x equals 0. Be negative e squared minus 1. That'd be like around, what was that, 7.3, so like 8.3-ish. Okay. Okay, let's try one of these with a fractional base. And I need more room. I'll go ahead and move this down. Okay, so let's think about this guy for a second. So the base graph would be a third to the x, like that. Okay, now you see that exponent? That one's the interesting one because that too is affecting x. Remember, x things happen opposite of how they look. So that'd actually be a horizontal compression. I mean, in terms of a rough sketch, it's a little hard to visualize. It'd just be making the graph skinnier. And then would I have to multiply the whole function by 4? That's multiplying the y's by 4. It's a vertical stretch. So again, the graph gets even skinnier. Okay, so really roughly, I mean, it's going to look something like that. Okay? But no shifts. So there are no shifts. So the number that makes the exponent 0, well, that's just 0. So I'll put 0 in the middle. Let me plug that in. That's 4 times 1. Now, if I put, if I put 1 in here, let's see, I get a third and then squared. So that'd be 4/9. So I'm kind of thinking because of that 2 there, it might be nice to put a half in. Because if I do that, then I get my power of 1 here, and I end up with that 4/3. Same thing here where I might want to use -1/2. 4 times 3, 12. So you see, this one's really steep. 2, 4, 6, 8, 10. I'm going to do this for the scale. I'm going to make this -1/2. I'll label this -1/2, 12. And then 0, 4. And then 1/2, 4/3. And then there's no shift up or down, so the horizontal asymptote would remain at y equals 0. It's really steep exponential. Domain, all real numbers, range 0 to infinity. How do I turn that guy red? So the other thing in this section is a little application of exponential. So you've seen this before in algebra. Okay, so these are the problems where what we're doing is we're actually looking at investment problems. I'll leave it red. So Here we have find the final amount after 4 years of an investment of $6,000 at an annual interest rate, 3%, compounded continuously. So the formula for an investment compounded continuously, we call this one the PERT formula. So compounding the interest continuously is the best way of all, because if you had an investment where interest was compounded like monthly, that means you'd have to wait a month before your interest was added on and you'd start earning interest on the new larger amount. If interest is compounded continuously, that means that additional interest is added in immediately. So you're immediately earning interest on the largest amount possible. So this PERT formula is for continuously compounded interest. Okay. And so the A is the final amount. The P is the principal, the initial amount. The R is the rate. Now you have to enter this as a decimal. And then the T is, of course, time. Now with these problems, with these money problems, the time units are always years. That's because they give me an annual interest rate. Okay? So that means I need to enter the time in years. So let me try setting up this formula for number 1 here. Find the final amount after 4 years of an investment of $6,000 at an annual interest rate of 3%, compounded continuously. So the initial amount, $6,000. The interest rate is 3%. The time is 4 years. So actually, that's a nice test answer. That's an exact answer. So the rule of thumb, I'd say, for how much to simplify these, what I do is I say, if the calculation is simple enough, I can do it in my head, I should go ahead and do it. So you see how that exponent, I should be able to multiply of like 3 cents times 4. That's 12 cents, right? So here's my exact answer. That's a test answer. Okay, so then I could enter that in a calculator. Let me just see what at least one of these comes out to. Let's see, so I would use the e to the x buttons. I have 6,000 e to the 0.12. Get about 6764.98. So that's an approximate answer. Okay. Let's try one more. Okay, so this one, same formula, but it says how much needs to be invested now to have 2,500. So 2,500 now is the final amount. Okay, so the final amount, I'm looking for the initial amount. The interest rate is 0.0125 and 3.5 years. So I have to solve for the variable, which is p. So I just have to divide. And that's it. So actually, I mean, I can't do that calculation in my head. I would just leave that as it is. So that's a nice test answer. I could do this on the calculator and just see what an approximation would be. I get 2,392 and 98. Okay, so this is the test answer. It's an exact answer. And then this is an approximate answer, an estimation. And we're going to look more at this formula in just a couple more sections.